Chapter 14, Correlation Regression. I'm going to model one item or one problem from beginning to end using correlation and regression. So I'll use the same data to demonstrate correlation and regression using problem 9 and then problem 25 from the end of the textbook. So researchers report that the results of a study demonstrating a negative relationship between weight and income for a group of women professionals. Following are data similar to those obtained in the study. To simplify the weight variable, the women are classified into 5 categories that measure actual weight relative to height, from 1 thinnest to 5 heaviest. Income figures are annual income in thousands, rounded to the nearest 1,000. We're asked to calculate the Pearson correlation for the data. So just by looking at the relationship, we see that 1 here is denoted as being very thin, and we see that it's related to a very high income, whereas the individual with the highest weight category of 5 showing lower income. So we can already affirm the relationship that was hypothesized when they indicated that there's a negative relationship between the two. From our reading, we recognize that we can either have positive correlations, both variables moving in the same direction, both increasing or decreasing, or a negative correlation, which means that as one increases, the other one decreases. So here we are seeing a negative correlation just by looking at the raw data. And here we can identify how many individuals were part of this particular study. So each individual gives us their weight and income. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we know that n is equal to 10. So we have 10 women. Again, they give us an x variable and a y variable. So this is our first chapter where we're seeing the data collected to test a relationship are coming from the same individual. So they're giving us 2 values. So we're asked to calculate R, and we learned from our reading that R represents the covariability over variability of X and Y separately. It's kind of similar to the F ratio when we're looking at the variation between groups over the variation within groups. Now here the numerator represents how these 2 variables are moving together, how they're related, and as one changes, how does the other one react? And then the denominator expresses the variation that we see that simply occurs in that X variable or Y variable that is as a result of chance or random selection. So the numerator represents how they're changing together. Again, covariability. If one changes and they're related, then we would suspect and predict that there would be a concurrent change in the other variable. And again, the denominator just represents their independent variation or variability with each variable being measured. And in this chapter, we're going to apply what we refer to as the definitional and computational formulas for sum of squared deviations. These are skills that we learned back in chapter 4. However, we have not used the definitional formula for SS very much, but in this chapter, it seems to be a better and easier or more efficient manner in which we can calculate SS because it leads to these other variables needed for correlation. So what I'm going to do is demonstrate the definitional and computational using this data set. So let's just recall what the definitional SS equation looks like. So it's SS is equal to the sum of X minus the mean of X squared. That's also the same as saying SS is equal to X minus the mean. Whoops. I need my summation notation. The summation of X minus the mean of X multiplied by X minus the mean of X. right? So we're squaring it. So it's the same thing. I'm using this so that we can see the similarities with the SS for the covariability, we refer to as sum of products. Now we have a second variable, so we would say the sum, and this would be x. SS for y is equal to the sum of y. Again, y would just be the variable minus the mean of y squared, or the same as saying SS is equal to the sum of y minus the mean of y multiplied by the mean deviation, because we're squaring that value. Again, by definition, SS represents the sum of squared deviations. In the parentheses, we recognize that that represents deviation. So we'll be using this to then compute the definitional equation for SP. SP refers to sum of products of deviations, to be more precise. So our equation, our new equation, is very similar to our SS definitional. It's the sum of our x minus our mean of x multiplied by y minus the mean of y. So notice the similarities. Instead of squaring the same value, we're taking the mean deviation for our x distribution multiplied by the mean deviation of our y distribution. And notice how it's similar to what I wrote over here. Again, we simplify it by just saying we square it. But if we were to stretch out this information, we would see that it's one mean deviation multiplied by the other mean deviation. And that's similar to what we're seeing here for SP, the sum of products of deviations. And therefore, our R is equal to what we refer to as SP, which represents covariability, over the square root of our SS for X multiplied by SS of Y. So we're going to use this equation to solve for R to see if we have a significant R value. Again, R can fall within the range of -1 to +1. The closer it is to -1 or +1, the stronger the relationship. Values centering close to 0 indicate that there's no relationship or a very weak relationship. The negative and positive just tell us what type of relationship we're looking at. Are they moving together in the same direction or in opposite directions? So using these equations, I'm going to show you the data that I've set up in an Excel worksheet, which I have also posted on Blackboard for you to follow along with. So what I've done is taken the data that was presented, and we see that over here. We have our X and our Y values. And then I created a scatter plot to see the visual interpretation of what we're looking at. So on the abscissa, we have the weight categories from 0 to 6. And so as we see this increase, the weight categories increase, we see a decline in income. So this is our ordinate, which represents our Y value, and in this case, the income of these women. And so we see that as our X variable increases, our Y variable decreases. Or if we look at it in the opposite direction, as our X value decreases, right, from the heavier category to the lighter category, we see an increase in income. So again, affirming that this is a negative correlation. And we can see that visually now with our scatter plot, which is very helpful to construct. You can do it freehand or use Excel to create a scatter plot, and it's a good visual interpretation of the data to see the pattern and to see the relationship. So at this point, I know that my SP value must be negative because there's a negative relationship. That is, one increases, the other one decreases. So that's a good thing to point out before you start to do your calculations. Then what I have here, so I've taken all my X values, and this column are my mean deviations, where I've taken my first X and then subtracted the mean. So of course we're going to need to calculate the mean of our distributions first. So let's do that before anything else, so you understand where these values are coming from. All right, so if I were to take the sum of X, so for calculating the average weight category, it's my sum of X over N. And if I were to take the summation of my X, we get 30 and divide by 10. So we have an average weight category of 3. The same can be done for the mean of our income. So the sum of y over n, and we get the sum of y equal to 660, which is, again, represented in thousands, so it's 66,000. And divided by how many? We have, 660. So we have 66,000 as the annual average income. Okay, so again, the average income is 66,000. I may have said this wrong a minute ago. The sum of y is 660,000 divided by 10. We get 66,000, representing the average income of these women. And that's important, of course, when we're calculating the mean deviation. So this -2 we see up here, this -2, is derived by taking our x, 1 minus 3, and that's how we get the -2. And we do that for all our x values. We take 2 minus 3, we get -1. 4 minus 3, we get 1. And so that helps us complete the mean deviation column for our x variable. We do the same for y. We take 125, which is our first y value, subtract 66. Again, these are thousands. 125,000 minus 66,000, and we get 59,000. So the second column represents the mean deviation for our y distribution. Okay, so we need to understand where those values are coming from. We've learned that if we take the summation of these values, they will always equal 0. They cancel each other out. So what we have to do is square all of those values. So we'll see here in this column represents all my x mean deviations that are squared. So -2 squared gives us 4, -1 squared 1, so on and so forth. And down at the bottom is the sum of all of those mean deviations that have been squared. Similarly, here in this column, we've taken all our y mean deviation values, squared them, and taken the summation. So essentially down at the bottom, again, what we've utilized are these equations. So SS is equal to the sum of our x minus the mean squared. And in this case, that's equal to 20. We've taken all our mean deviations, squared them, and taken the summation, and that's what that 20 down there represents. And that's for our x distribution. For y, SSY is equal to the sum of y minus the mean of y squared, and there we get 7,430. So we've calculated our sum of squared deviations for each variable. Now over here, again, our ultimate goal is to calculate all the values necessary for our R equation. And the numerator of our R equation, again, is SP, the sum of products of mean deviations, over SSX multiplied by SSY. So we have the values for our denominator. And now for our numerator, the sum, using our definitional equation, SP, as I just showed you on the previous slide, is the sum of our mean deviation for X multiplied by the mean deviation of Y. So we have our mean deviation of X here, the mean deviation of Y, and so this column over here on the far end, these values, right, is the product of those deviations. So the first one here, -2 multiplied by 59, gives us -118. The next one is -1 multiplied by 12, and we get -12. So again, we're following this. We're calculating our mean deviation for X, mean deviation of Y, and we're multiplying them. And then sigma says take the sum of all of those mean deviation products. So we're multiplying those mean deviations and then taking the summation. And that's what this value represents. So we've done all of that, and that's equal to -359. So now we have all of the values necessary to calculate our value, which is our Pearson correlation coefficient, to affirm how these variables are moving and together, if at all, and then how strongly they're correlated. So again, the numeric value indicates the strength, the sign indicates the type of relationship we're looking at. All right, so R is equal to the covariability over the independent variability of each variable. So we have all of these values. So our sum of products, sum of mean deviation products is equal to negative 359 over the square root of 20 multiplied by 7,430. Okay, so in our calculators, go ahead and calculate this value. Let me do it step by step. So we have negative 359. Again, if the numerator is negative, that's affirming the type of relationship. And we had talked about how as weight category increased, income decreased. So we should see a negative value for the covariability expressed in SP, and indeed we do. And that's divided by 385.4867. And that gives us a R value equal to negative 0.931. So again, the sign affirms the type of relationship. As one variable increases, the other one decreases, and the value, the numeric value, expresses the strength. So we're looking at a very strong, so this would indicate a very strong negative correlation just by our understanding of the range of R that are possible and our understanding of the type of relationship denoted by the sign. However, we can't completely affirm that this is a strong negative correlation until we put it to a hypothesis test, which I'll demonstrate in just a second. We'll use a t-test to determine if this R statistic is truly a strong negative correlation. Just assessing its face value, that's what we would consider to be a very strong negative correlation because it's so close to -1. All right, so on the next slide, I'm going to show you the same calculation, but we're going to use the computational process to calculate SS for each X, for the X variable and for the Y, and then the SP, the sum of products of deviations. All right, so this is the computational process. We've learned and have been using this equation quite a bit since chapter 4. So SS for X is the sum of X squared minus the sum of X squared over N. And we would do the same for Y, but before I do that, let me just show you what this is actually indicating if we were to write it in a different format. So the sum of squared deviations of X is the same as saying the sum of X times X minus sum of X multiplied by the sum of X over N. So these are equivalent to one another. Again, instead of saying X times X, we just say X squared here, and then in parentheses, the sum of X, we're going to square that, so that would be the same as saying take the sum of X and multiply it by the sum of X. I want to show you that so that we can see the similarities with the SP computational formula. So we would do the same for Y. The sum of Y squared minus the sum of Y squared over N, and that's equivalent to saying we're going to take the sum of Y times Y minus the sum of Y multiplied by the sum of Y over N. And finally, that leads us into our new equation, the computational formula for SP. And that equation looks like this: the sum of X multiplied by Y minus the sum of X multiplied by the sum of Y over N. So again, notice the similarities Here, because we're only using y, we see y times y, but now we're talking about how these variables are moving together. So it's the sum of x multiplied by y. So it's helpful to see the similarities and understand the notation. Now that we've done that, we can use our equations for this SS for x and SSY to calculate our SP, the sum of products of deviations. So we'll begin with SSX. Here again we have our original x values over here on the left, and then we have the sum of x, and then we have our y, and we have the sum of y. And over here we have x squared, which is simply taking our x values and squaring them. So therefore the 110 represents the sum of x squared, all of our x values that have been squared. Similarly, y squared, all of our y values have been squared, and then here represents the sum of all those squared values. So given that, we can calculate SSX, which is the sum of all x values that have been squared. That's this, not that value, excuse me. It's the 110 minus the sum of x, that's 30. I'm going to square that, and we have 10 values. So if we do the calculation, 30 squared divided by 10 subtracted from 110, SSX is equal to 20. And this should look familiar because that's the exact same value it equaled using the definitional formula. So we should get the exact value. There should be no differences. If there are, then somewhere in our calculations we've gone wrong. So we get the same value. Now we can calculate SSY. So it's the sum of all y values that have been squared. That's this value. So it's 50,990 minus the sum of y, which in this case is 660. Again, this value here. We're going to square that and divide by 10. So in our calculators, take 660, square that, divide it by 10, and subtract it from 50,990. And we should get the same value we did using the definitional formula. So 7,430 is what we should see in our calculators. So again, we're getting the same answer using a different process. We're more accustomed to using the computational formula. However, given the equations for regression, the definitional formula seems to be more efficient, but you can use either. In fact, you need to know both to answer the homework questions. So again, this example showing both processes will help you with any data set that you're presented with. And now we can calculate SP. So again, SP is the sum of x multiplied by y minus the sum of x multiplied by the sum of y over n. We can replace variables. So we need to explain this last category. This last column is xy. So what I've done is simply taken my x value, 1, multiplied by my y, get 125,000. So that's 125 here. 2 times 78 gives us 156. So I've done that for every x and y. And then down at the bottom here is the sum of every x multiplied by its corresponding y. So the sum of x multiplied by y, we get 1,621 minus the sum of x, we know that that's equal to 30, multiplied by the sum of y, which is 660, over 10. Okay, so take 30, multiply it by 660, divide it by 10, and subtract it from 1,621. And we should see that we get the exact same SP value as we did with the definitional formula. You should get on your calculators negative 359. So again, we can use either set of equations as long as we don't mix and merge them, keep them separate, definitional or computational, and that will lead us into the same answer for our sum of squared products, excuse me, sum of mean deviation products. So we're taking the mean deviation, multiplying them to get the sum of products of mean deviations. But again, in this computational formula, we don't see mean deviation being calculated. So in the definitional formula, we see mean deviation, and it's much easier to understand conceptually. The computational formula is a little faster, but again, when we get to our regression equations, the definitional formula may be a better one to use. All right, so since we ended up with the same SSX of 30 and SSY of 7,430 and SP of negative 359, our R value should not change. So again, we have negative 359 over the square root of 30 multiplied by 7,430. And we've calculated an R value equal to negative 0.931. So again, all of those statistics were equal using definitional and computational, which would obviously lead to the same R value. And at face value, we see that this is a very strong negative correlation. Even though we weren't asked to, we should calculate also the R squared. So R squared is referred to as coefficient of determination. And so we would take negative 0.931 and square it. So in our calculators, R squared is equal to, in our calculators, 0.931 multiplied by itself, and we get 0.867. So we can interpret that as 86.7% of the change in income, our Y variable, is attributed to or as a result of the relationship with our X variable weight. So 86.7% of the change that we see in income is associated with the relationship with the X value weight. Now keep in mind that that's not within one person's lifetime. That has to do with one observation to the next, one female's weight and income in comparison to the next weight and income from a different observation, different individual. So again, it's the changes that we're seeing from one pair of data points to the next pair of data points. And if we see that the weight category decreases, then we understand that there's a really high probability that the change in income will follow suit in the negative direction. So, or positive direction in this case, if the weight decreases with the next female or observation, that we'll see an increase in the Y variable, which is the income. So again, coefficient of determination, percentage of variance in one variable explained by the relationship with the other variable. All right, so 9b says, is the correlation statistically significant? Use a two-tailed test with alpha at 0.05. So again, at face value, it appears to be a very strong correlation between these two variables, given our R statistic of negative 0.931 and R squared equal to 0.867. We're looking at very strong negative correlation, but we cannot draw that conclusion until we put this statistic to the test. So we're going to conduct a t-test, and our hypothesis, our null hypothesis says our Greek letter rho, and that's representative of the population correlation, is equal to 0, that we see no relationship between these two variables in the population. Rho is equal to 0. The alternative research hypothesis says that rho is not equal to 0. It's not equal to 0, that we do see a relationship between these two variables. So again, we're going to conduct a t-test to determine the significance of this R statistic, the Pearson correlation coefficient. So we need to know what our critical t-value is. We're going to identify degrees of freedom. So for correlation, it's n minus 2. In this case, n was equal to 10 minus 2, and we get 8. Again, we're going to use a two-tailed test with alpha at 0.05. So we need to locate what our critical t is equal to in our t distribution. So here's our t-table. We have degrees of freedom of 8, two-tailed test at 5%, That's here. I'm going to see where those intersect, and we get a critical T of 2.306. So our critical T, given the values of our table, is positive negative 2.306. So we can visually set these parameters. Again, in the center is represented by rho. It says that the correlation is equal to 0. We have negative 2.306, positive 2.306. Our critical region is set in the tails. And now we're going to calculate our T to see if it falls in the critical region. Our T equation for testing significance of a correlation coefficient is as follows. So T is equal to our correlation coefficient minus rho over what we refer to as the standard error, and that's calculated by taking 1 minus our coefficient of determination over degrees of freedom, and taking the square root of that value. So let's replace variables. We have our R statistic equal to negative 9.31, rho is equal to 0, and then we have 1 minus R squared, we calculated that up here, 0.867 over 8. Okay, so let's simplify this. We have negative 0.931 over, our denominator now is represented as 0.1289. That's what the denominator is equal to. So 1 minus 0.867 divided by 8 and take the square root. We get 0.1289. And now we take negative 0.931 divided by 0.1289 in our calculators, and we should get 7.22. Negative 7.22. We can use that, and then we can assess where does that reside in our T distribution and in relation to the critical T. And so we would conclude that's way over here, that our T statistic is very significant in affirming that we do have a strong negative correlation between women's weight category and their income. So now we can draw our conclusions. Okay, so we know we're going to reject the null. The null said that there was no relationship between these variables. We know we're going to reject the null, and results indicate that there is a significant relationship between women's weight and income. And we would report our R statistic, which is equal to negative 0.931. We'd identify the sample size, n is equal to 10. And our probability statement, p is less than 0.05 because it was significant. Identify the tails of the test, so we conducted a two-tailed test, and include our supporting statistic of R squared, which was equal to 0.867. So again, using data reflective of some other actual research testing the relationship between these two variables, it's a sad commentary on our population or society or culture that the relationship between women's income is attributed to their weight, and we're seeing it's a very strong negative correlation. However, we must recognize that we are not saying that a woman's weight causes her income. We recognize that there are other variables at play. So things that determine someone's income relate to their education, skill set, the career they're in. All of these things contribute to a person's income. but it's our culture and the influences of it that establish this relationship between these two variables. There's a problem in the homework that does the same test of relationship for men. And interestingly, there is not a relationship between men's weight and their income. In other words, men can be any shape or size, and their income is not tied to that. But for women, it is. And this should be a motivator not to start a diet, but instead to recognize that we create culture, and the symbolic interactionist within sociology states that if we create something, we can uncreate it. So it behooves us to diminish this relationship that we see and focus on the other things that attribute to someone's income, and make those things much more valuable, such as skill set, education, motivation, the career that they're in. All of those things are significant. Nonetheless, it's an interesting example to see mathematically how we would affirm this relationship, but again, recognize that if this relationship exists, we created it and we can uncreate it as well. I'm going to use, again, the same data to show and illustrate the regression equations, which is the second part of this chapter.